So good afternoon, everybody here and also those on YouTube. It is a pleasure for me to introduce today's guest. So we are hosting Professor Franz Baader from the Technical University of Dresden. He's been a full professor there for some time, 20 years. And he's well known for his work on description logic, and the author of the Handbook of Description Logic, and more recently, the Introduction to Description Logic Handbook, which I use very often in my courses. And one thing that strikes me is that his co-authors are his PhD students who are now themselves professors and very important. So most of the important people in the area came from his group. He's also the director of the Institute of Theoretical Computer Science there at the TU Dresden, and a member of the International Advisory Board here of the Center for AI. So he will give his view on description logic, and I would like to welcome you on board.
So thanks a lot for inviting me. It's a real pleasure to be here. So I will take you on a description logic journey, and basically we are going by ship. I'm your captain. I promise that I'm less drunk than I was when I was there. This was at a conference dinner in Vienna, where we were giving fancy hats and lots of Heurige, which is the wine of this year, basically. So, how does it start? I mean, description logic is a sub-area of knowledge representation. And let me start with citing Ron Brachman and Daniele Nardi. They've said what knowledge representation is about. So they said this is about developing formalisms for providing high-level descriptions of the world that can be effectively used build intelligent applications. Whenever I read such a sentence, I say, what? Okay, what do they actually want to say? So first of all, they talk about formalisms. So this means you need a well-defined syntax, so you need to know what are you allowed to write, so it's sort of restricted. And then, of course, you also need a formal, unambiguous semantic. Now, I would hope that nowadays one says, well, that's clear, we need that. But when Ron Brachman started his work, this was in the 70s somehow, this was not so clear. I mean, there were lots of formalisms around that maybe had a syntax, but definitely didn't have a semantic. So in that sense, this is something very important. We want to have this semantics. When they say high-level descriptions, they mean we only want to represent the relevant aspects of the application domain. I mean, it's not like we are now philosophers that are thinking about a certain notion and we want to model this notion in all detail, but we say, well, what's actually relevant for our application, and we model those aspects. And the others we just leave out because they are not relevant. And well, intelligent application, intelligence means you are able to reason about the knowledge you have. You are able to draw conclusions. So in that sense, we now have seen what this sentence probably means. Effectively used, of course, also means that we want to do this in practice. It's not just that we want to represent knowledge, we want to reason about it, and that should work in practice. So we should get answers in a time that's acceptable in the application we have. So that's the general goal of knowledge representation, as stated by Brachman and Nardi. Now, description logics, as I said, is a sub-area of knowledge representation where we want to represent terminological knowledge. So we want to be able to define the important notions of an application in an unambiguous way, so that everyone knows what this means. if you start with the demand that you want to have a formal unambiguous semantics, very often you end up with logic as the way of defining the semantics. Even if you start like in the settings where description logics came from, people had formalisms that syntactically didn't look like logic, but once they started to think about how to formalize the semantics, they noticed, okay, I just do it using first order logic. And of course, to be effectively used, we want to have decidable fragments, so where we can really implement the reasoning. There's also, for people that know what modal logics are, there is a close relationship to propositional modal logics. So some of them are just syntactic variants of each other with the same semantics. So you can transfer results between these two. If you don't know what modal logic is, I won't mention it again. The design goal in description logic was always to get a good compromise between expressivity, so what you need to express in your application domain, and the complexity of reasoning. Because if you want to draw consequences, it's important that you can draw them fast enough for your application. Now, for that reason, because we had this emphasis, there are now many decidability and complexity results for many different description logics. So there's not just one description logic, there are description logics. So the plural S makes sense here. There are lots of them. And there are also implementations of practical systems, not just theoretical investigations of the complexity. And basically, these systems come in two varieties. On the one hand, we have systems that can deal with very expressive description logics, so where you can express a lot of stuff, but where you have to pay for it by having a high worst case complexity, but where well-implemented systems still work quite well. And here are a few names of systems, so older ones like Fact and Razor. So Fact was the first one that was really fast for expressive description logic. Here's some other names. But there are also inexpressive description logics where reasoning is much faster and which are still enough for certain applications. And for those, there's also a few names of systems here. For those, you have much faster reasoning. And nowadays, there are also some systems in between that have a pay-as-you-go behavior. So basically, if you use them on these inexpressive description logics, they are as fast as the dedicated systems for the inexpressive logics. And the more features you use of expressive languages, the slower you get, but you have to pay for the expressiveness. Now, applications in the beginning, the main motivation came from natural language processing. But in the end, it turned out that it's actually also very useful in more technical applications. Like at AT&T, they use description logics to configure telephone switches. Databases have use for description logics. We had lots of applications in engineering domains. Why? Because I'm at a technical university, so there the engineers are the important people, so you, of course, cooperate with them. And the kind of killer application came with the fact that the World Wide Web Consortium standardized a language to define ontologies, so OWL, the web ontology language, and also biomedical ontologies are written in description logics, and in particular in these inexpressive description logics. So you can say, well, we have the theory, we have the implementation, and we have the application. So it's a very good situation, but of course we had to work hard to get there. And on this journey, I want to somehow show what happened in the last 30 years or so. But before doing that, I mean, I now talked about description logics. Now let's get a bit more into detail. What are actually description logics? but we still start in a very general way. So the important notion is a concept. We want to define the important notions of the application domain, I said, and these notions we call concepts. Now, in a description logic, you can build complex concept descriptions. And for that you have constructors. So you have constructors that allow you to build complex descriptions of concepts. And this is based on using what we call atomic concepts, which for logicians are unary predicates, and roles, which for logicians are binary predicates. Now at the moment, just remember, concepts are then interpreted as sets of objects. So if I have an interpretation of these symbols, a concept will be interpreted as a set of objects. And once we have the concepts, we can use them to define knowledge. But in the beginning, concepts are just descriptions of sets. That's not so useful. Now we want to do something with them. And what we do in description logics is we state inclusion relationships between concepts. So we call such inclusion relationships, this is C is contained in D. We call these general concept inclusions. Why? Because before we had not so general concept inclusions. And so they are just of the form C contained in D, where C and D can be arbitrary concept descriptions. And remember, the semantics gives us for every concept, if I have an interpretation, a set. And what does C contained in D say? Well, it says that I want interpretations where Ci is contained in Di. And the interpretations that satisfy this we call models. A boxes then talk about specific application situations. So, because until now we talked only about concepts, so terminological stuff. So here we can talk about specific individuals and can relate them to concepts and relate individuals to each other using roles. And again, I mean, what is the interpretation of this? So if I say C of A, I want to say A should belong to C. So in an interpretation that is a model, then the interpretation of A must be an element of the interpretation of C. Okay, this way you now, in principle, know the semantics of T boxes and A boxes, but I still was hiding how do we actually build these concept descriptions. And, let's not forget, if we have a T box and an A box, we call it an ontology. And what I also forgot is I also wanted to mention we have restricted forms of T boxes. That's why the other ones are called general concept inclusions. And these are just concept definitions. So we say concept name A should be equal to concept description D. Yeah? And of course, this semantic says A must be equal to D in every interpretation that is a model. So we'll come back to these restricted forms as well. But let's be more concrete now. I mean, now I want to introduce a specific description logic that's called ALC for some historical reasons. It stands for attribute language with complement. So it has certain constructors which are written here on the slide. So top, negation, conjunction, disjunction, extension, restriction, and value restriction. And let me try to illustrate this by one example. So assume we are in a setting, a university setting, and we have courses that are can be attended by students, and students can be smart and studious or not. They can have topics which might be easy or not, and of course they also should have a teacher. So I want to talk about an advanced course that has a smart or studious student, no easy topic, and a teacher. So how can I do that? I say this is a course. Now course is a concept, an atomic concept that is advanced. Advanced is also an atomic concept. to say it has a student, I use a binary relation, a role has student, and say there is a student, and this student should be, well, there's an error here, who sees it? So I say smart or studious, but on the slide I say smart and studious. Yeah? So I use the and on the right, but or on the left. Which means probably that I don't have an illustration of how to use an or, but just assume that, so imagine this here is turned around and it's an or. All the topics are not easy. So here I use the value restriction and the not. And it has a teacher without any properties stated for the teacher. That's how I use the top concept. It's just something. No special properties required. Okay? Now in a T-box, for example, in this simple one with concept definitions, I could define a good course to be a course that has some properties, so maybe those properties. Yeah? Now a general concept inclusion could, for example, say, if something has a student, then this is a course. Which would mean that if we have this, then in our example concept, we could actually leave out the course, because this follows from the fact that it has a student. Now in the ABOX, I can of course say that a certain course is a good course, I'm its teacher, and the topic is description. Now I talked about has a well-defined semantics, so we need to have the unambiguous semantics. I don't want to emphasize this here, but here you see how you in principle define the semantics. You define the semantics of the constructor. So here I say, okay, this square intersection sign is interpreted as set intersection. Existential restriction, if I say there exists an R in C, then this collects all the Ds that have an R successor E, so the DE should be an Ri, and such that the E then is a C. And the for all is sort of dual. Then I say whenever I have an R successor, then this R successor needs to belong to my C. So this way we then define, so if you introduce a description logic constructor, you need to define it in this way, which allows you then, if you have a complex concept description, to find out which set is assigned to it in every interpretation. Okay, now remember we defined the notion of a model, and in logic, as soon as you have the notion of a model, you know how to define reasoning. It's always logically something follows if it holds in all models. And we just do this now in a special setting. So subsumption, we want to know, is C a subconcept of D? So, and I say C is subsumed by D with respect to the T-box T, if this holds in all models. So if Ci is contained in Di for all models of my T-box. Concepts can be contradictory. I mean, you have already seen on the previous slide, I mean, you can make an error when you write concepts, and maybe you can make a worse error than I did and make the concept unsatisfiable. So it's total nonsense. There cannot be elements of the concept. Yeah? And this is what the satisfiability is about. Yeah? So I ask, is it possible to find an interpretation in which this is non-empty, this concept? With respect to the T-box, I of course say, is there a model of the T-box where this concept is non-empty? Now, of course, A-boxes can also be contradictory. And this is the question, does it have a model, which is also a model of the T-box? And the instance problem talks about whether an element E belongs to a concept C with respect to our knowledge base. So we say that the A box A entails with respect to the T box T that E belongs to C. Well, if, again, this is true in all models of A and of T. And so these are just the general instantiation of the general thing. Something follows if it holds in all models. Now, of course, if you want to implement a description logic system, fortunately, you don't have to implement 4 algorithms. It's enough to implement 1 algorithm because these problems can be reduced to each other. At least if you have negation, well, and conjunction, but we always have conjunction in description logic. Yeah, because so it's easy to see that subsumption and satisfiability can be introduced to each other, and also consistency and instantiation, and satisfiability can be reduced to consistency, but in general, not the other way around. Also, for a lot of description logics, you can also do it the other way around. But there are examples where you can't. So this means if you have a logic that has conjunction and negation, then it's enough, for example, to implement a consistency algorithm for A boxes. Then this solves all the problems. Now, I already mentioned this on one of the introductory slides, but just to emphasize this again, the main emphasis in DL research was on developing reasoning procedures. Because, if you have such a language, it's only useful if you can also reason effectively. And so this gives you this trade-off between complexity and expressivity of the language, yeah, because on the one hand, the application relevant concepts must be definable, otherwise you cannot use this description logic. And some domains really require very expressive description logics. On the other hand, of course, reasoning must at least be decidable and preferably of a low complexity. And this again requires you to restrict the language. So you would want to not use a monster description logic if you don't really need it, because the monster description logic would have slow reasoning procedures. But again, you also should be aware that this complexity stuff is mainly theory, and in the end we want to have practical algorithms. Yeah. And that means they should behave well in practice. In the application we have at hand, they should at least be fast. Even so, in the worst case, they are not. And of course, it's also nice if they are easy to implement. It doesn't take years to find a good implementation, but it's relatively easy to do that. So that's actually what we are trying to do. Yeah? We're trying to find a good compromise between expressivity and complexity. And then if we have found a language that gives a good compromise, we want to get these practical algorithms. Now, of course, in the beginning, you should start small. Yeah? So when we now start our journey, we now know what description logic are, what's the major concern. So let's start very small. A description logic that for historical reasons is called FL0. It has conjunction, value restriction, and top. So it's a sub-language of ALC that we have seen. And in the early days of description logic research, FL0 was considered to be the smallest description logic ever. So, because you need conjunction, because you need to be able to state that something should have several properties. Without that, you cannot really define things. And then the value restriction was sort of a decision made at the beginning. Now let's explain that. So this is one of the early formalisms called semantic networks, which was one of those things that didn't really have a semantic. So it was called semantic networks, but they didn't have a semantics. And so what does this network say? I mean, it says a frog is an animal and its color is green. Yeah? So sort of intuitive what it means. But there are certain ambiguities here. So what do I say when I say frog have color green? There's as one possibility where I view this as what we call in description logic a value restriction, where we say the only possible color of a frog is green. So a frog is an animal and every possible color this frog has is green. Okay, now this is a frog that's only green. I mean, it's very hard to find frogs that are only green. I mean, this one also has some black and some white, but black and white are not colors. Yeah? So this I was told in my art courses. Black and white are not colors. So this is a frog that, yeah, well, maybe there's some yellowish stuff there. But anyway, yeah, so this is a value restriction frog. Yeah? But it could also be an existential restriction frog where you say, okay, this could mean one of the colors must be green, but it could also have other colors, like this one. Red and blue, and yellow. So this would be the existential restriction reading. And in this early system called KL1, which is the predecessor of all description logic systems, they made this decision that these property links in semantic networks are interpreted as value restrictions. So green frog, only green. Okay. Now, so this is the smallest possible description logic. And now the German complexity people brought several bad news to the community. This was before my time actually in description logics. I was already a PhD student, but working on other stuff. What people wanted KR systems to be is very efficient, so they said reasoning should be tractable, possible in polynomial time. And so that was the requirement. In addition, the requirement was at least FL0 for these kinds of systems. This KL1 system, and also early successor systems like Beck, which was done at TU Berlin, Mason, which was done, I think, at Philips. KREP was actually done at IBM, somewhere in New York way. They employed polynomial time algorithms, so everything fine. But then came along Manfred Schmidt-Schaus, and he showed that KL1, the language used there, is actually undecidable. And Bernhard Nebel showed that even for this smallest possible description logic, FL0, reasoning is intractable, so not polynomial time, if you have this simple kind of T-boxes. Yeah? So really bad news. Now you could say, but isn't that a bit strange? I mean, am I not inconsistent on this slide? Yeah, because I say reasoning was done in polynomial time, but it's actually, there is no reasoning algorithm for KL1, and for all the other ones, it cannot be in polynomial time. Yeah. Well, the reason was that these algorithms were sound but incomplete. Yeah, so when you ask them a subsumption question and they said yes, that was true, that's soundness. But when they said no, it was more like don't know. Yeah, it's not the case, the subsumption doesn't hold, it's just, I couldn't find a subsumption. Right, now let's look at the complexity. So we look at the case without any T-box, just a subsumption between concepts. We look at acyclic T-boxes, which are special kinds of concept definitions which don't have recursion in there. There are cyclic T-boxes that have recursion, and there are the general T-boxes. And in FL0, it's sort of a nice example of a description logic where in every step you get an increasing complexity. So without T-box, it's polynomial. With acyclic T-boxes, it's co-NP. With cyclic T-boxes, it goes up again to P space. And with general T-boxes, it's X. I'll say a bit more about these classes. Complexity classes at the end of this slide. For ALC, we have P space even without a T-box. Acyclic T-boxes don't hurt. Cyclic T-boxes or general T-boxes already throw you to text. And well, here are the references to papers where this stuff was shown. Now, just to remind you, so polynomial time is usually assumed to be solvable very fast. ONP or NP is stuff which is already, well, not so great. P space is even harder, and X time is definitely exponential, so no way around it. So P, we say tractable, X time definitely not tractable, and co-NP and P space, there we have this kind of thing, not tractable unless something revolutionary happens in complexity theory, like P equals NP is shown. Unless P equal NP. If not tractable, if P. Right. So this means only FL0 without T-boxes is polynomial, which is not so nice because we don't want to just have concept descriptions without T-boxes. But you could also read this in another way, and this is what we did at DFKI when we started to work on this. We said, okay, the knowledge representation people said conjunction and value restrictions they want to have anyway, and we want to have T-boxes, so we are probably here or here. Well, ALC is not much worse, so let's just take ALC, because I mean we have a lot more expressivity and we don't really pay compared to FL0. So you can also see this as positive. So there's no reason to restrict to FL0. You can go to more expressive logics. And so we got larger. Now, why would you want to extend ALC? So when I started at DFKI, the people had already worked on ALC, and they were looking at a very fine-grained analysis of the complexity of fragments of ALC. And I said, well, that's your playground, but I find it a bit boring. So let's look beyond. Yeah? And we actually had applications at DFKI then that required more. And let me give a few examples. One was concrete domain. So there we want to be able, when defining concepts, we may want to be able to refer to concrete objects, for example, numbers and predicates on these objects, when defining concepts. So this is like in databases, in your queries, you want to have what's called built-ins. Yeah? You want to be able to use numbers and comparison of numbers. Yeah, and here's a simple example. So I could define the concept of a teenager as a human whose age is at least 10 and at most 19. And here, age somehow refers to the age of a person, and it can compare the age of a person to some number. Or something a bit more complicated, I say, if I have a human, then the mother's age is always larger than the age of this human. So the child's age is smaller than the mother's age. And the same for the father. That might be interesting to find strange errors in your A-box, for example. If you have a child relation and you know the ages and you say, that cannot be, there must be something wrong. And so Philipp Hanschke and I basically introduced the language extending ALC where you could say such things, and we investigate this, and it was actually motivated by a mechanical engineering application, about which I will say a bit more in the next slides. Another thing, well, okay, Lutz and Milicic also had quite a lot of things to do, but let me come back to that later, because why the stuff Philipp and I did was not enough. You'll see on the next slides. Another thing we looked at was cardinality constraints. So that's a bit different. It's also using numbers, but it's a bit different from the concrete domains. So I might want to talk about the number of role successors. So for example, I might want to say that someone has at most 2 sons and at least 1 daughter. So I can say this person has at most 2 children that are male and at least 1 child that is female. So this is called number restrictions, but in a variant that had not been investigated before. But we could also want to talk about cardinality of concepts. So if I say something like, there's 45 million probably, counting the zeros, at most 45 million cars are registered in Germany. And this is then, in a certain sense, a generalization of a T-box statement, because it says something about my interpretation domain and how many individuals having certain properties can be there. And so we also investigated that, motivated by a configuration application we had. And my student, Stefan Tobis, was the one that found the exact complexity of this language, because we had an upper bound, but it was not so clear whether that was a tight upper bound, and actually it was not. Tobis could lower it. Another thing is transitive roles, sub-roles, and inverse roles. What's that about? Say I want to talk about an engine which is part of a car and has as a part a distributor. Then the role has part should be transitive. If I have a part of a part, then this is again a part. Has part and part of are inverses of each other. Yeah. And I could also have something like has strict part, which is then a sub-role of has part. So this motivates why we would want to have such things. And this we actually started to investigate, motivated by a chemical process engineering application, where the process engineers wanted to describe reactors and the parts of the reactors and the parts of the parts and so on. And this was also a beginning of a collaboration between Ian Horrocks and my PhD student, Uli Sattler, which basically resulted in the fact system. Ian did the implementation, but the language, the algorithms were developed in collaboration with people from my group. And what you can notice that these and some additional features are now available in this web ontology language, OL2DL. So they were motivated by specific applications, but they were so interesting that in the end they were seen to be of relevance for lots of applications. And of course, there are highly optimized reasoners for this language, like FactRaiser, Palette, Hermit, some of the newest ones, Sequoia. I have the ... so no one can complain that I forgot his or her reasoner. Now I want to say a bit more about these concrete domains. So why did we want them and what happened there? So the application we had at DFKI was actually to describe the geometric structure of rotation symmetric lathe workpieces. I mean, this picture there is a picture of a lathe workpiece. It's basically something that's round and where you have grooves in there, and you produce this with a lathe machine, which is this yellow thingy here. And these machines are controlled by something called CNC programs. And the idea was that from such a drawing of a lathe workpiece, we wanted to automatically generate a CNC program that produced it. And for that, we needed to have a formal representation of this workpiece. And the idea was to do this using description logics. And so let's look at a simplified version of such a lathe workpiece. So the idea is that we want to decompose this workpiece into simple geometric substructures, like this. So decompose it into simple geometric components. Then pull this apart, and then describe the geometric shape of the simple components, and also how neighboring components fit to each other using concrete domain predicates. So concrete domain predicates, we can refer to numbers and then compare them somehow. And we use their real arithmetics. So it's decidable but relatively high complexity. This was the idea. And then, of course, we want to describe the whole lathe workpiece, and there we just say that it's composed of these parts. So there's a first part, and then there's the next one, and the next one, and the next one, and so on. And for that, since we didn't want to have, say, only be able to talk about lathe workpieces consisting of 5 parts or of 6 parts, we wanted to have arbitrarily many parts. We wanted to be able to access the parts by doing the transitive closure over this next relation. So going to next, 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 next. So this is why we also wanted to have transitive closure of rows in our language. And the good news was that actually we could show that extending ALC was nicely behaved concrete domains, leaves reasoning decidable. In the setting without a T-box or with respect to an acyclic T-box, which was the kind of T-box that was usually considered then. And this admissible just means that reasoning in the concrete domain is decidable. Because in the description logics, integrating the concrete domain, of course, you can also express stuff that happens in the concrete domain, so you need this to be decidable at least. And I could also show in the same year that actually published at the same conference that extending ALC with transitive closure of rows also leaves reasoning decidable. So nice, but bad news, combining both extensions actually causes undecidability. So in the end, we have both things, but in combination it causes undecidability. So in the end, they used in the project, they used ALC with concrete domains and handled the transitive closure using logic programming, which in general is of course undecidable. So they put a programming structure on top of it to realize this. Now let me try to explain the undecidability proof. It's not hard because I actually found it while driving on the German Autobahn, and who has driven on the German Autobahn knows that it's kind of, you need to be attentive. Yeah? So let's look at the picture. Yeah? We have this lathe workpiece that's composed of certain parts where we can, with the concrete domain, describe the properties of these parts. They are linked by next, and we also can link the properties of the parts linked by next. Now assume you don't describe a geometric property of such a structure, but you describe the configuration of a Turing machine at one point in time. You can also do this relatively easily, say with rational numbers. You can encode the configuration of a Turing machine into one rational number. And with predicates over rational numbers, you can also say that 2 such encodings are ones that are successor configurations of the Turing machine. Well, and then with transitive closure, you can just say, well, is there a sequence of nexts such that you are in a terminating state? And so you have reduced the halting problem for Turing machines. So in principle, very simple. In detail, you have to work it out how this goes, but it's not hard. Okay, now more bad news. When Carsten Lutsch joined my group, he was very interested in concrete domains, and he wanted to have decidable variants, but first he showed some negative things. So for example, also acyclic T-boxes leave reasoning decidable. They increase the complexity. Remember for ALC, they didn't increase the complexity from no T-box to acyclic T-box, but for ALC with concrete domains, the complexity can increase. And if you add cyclic or general T-boxes, so it's not just transitive closure that can cause undecidability, also cyclic or general T-boxes can cause undecidability. And this is the case even for very simple concrete domains. So integers with some very simple operations. Say integers with addition, it's already enough to get undecidability. But of course, we still wanted to use description logics with concrete domains. So Carsten found conditions on the concrete domains that actually preserved decidability even in the presence of general T-boxes. And this condition is called omega admissibility. Now this is a relatively complex combination of several conditions, and so it was not so easy to actually show that a concrete domain satisfies this property. And in the original papers, there were two examples in 2002 to 2007. So there was just these two examples. Yeah? And no more were found. And in 2020, together with a PhD student, we actually found out how one can characterize this condition of omega admissibility in an algebraic way, and this allowed us to find new omega admissible concrete domains. So now we have a large variety of those, but most of them don't look as if you could use them in applications, but some of them actually are quite interesting. Okay, so what have we have done until now? So we were small, F0, we said, okay, it's bad anyway, so let's go to the expressive ones. At some point we got over the decidability line, but then could push it down again. And now let's look back at smaller ones. And this, how do you get there? Well, basically, we go back to our semantic networks and the semantics of property edges. Yeah? So KL1, they said it's value restriction, and they had to pay for it. Now we say, okay, well, let's use existential restrictions. And if we use existential restrictions, so this means this frog with many colors, yeah, then the logic we get is called EL, and then everything is nice. So let's look back at the complexity picture. So here you see for F0, it increases. For ALC, it's bad from the beginning. And for EL, it's nice. It's polynomial time, so tractable, very nice. And we actually, the first time we introduced EL in a paper in 1999, but only as an intermediate language. We wanted to go to more expressive ones, but then I was able to show that this leaves you in P for acyclic and cyclic T-boxes. And then one of my PhD students was able to show that even for general T-boxes, you stay in P. So it's much nicer. And of course, the question was, is EL useful in practice? So when I found these results, I thought, okay, well, nice theoretical results, but totally useless in practice, probably, because the language is so inexpressive. I told Ian Horrocks about this language, and he said, do you know that SNOMED CT is using EL? Okay, so SNOMED CT is a very important medical ontology. So EL is actually a practically useful DL for which T-box and A-box reasoning is tractable. So very nice language. So you have just seen in my table that subsumption in EL is polynomial even for general T-boxes. It is used in several biomedical ontologies. So SNOMED CT, the gene ontology, and many others. Tractability is very stable, so if you add avoxes, it stays tractable, and also if you add extensions of EL by additional constructors. So this tractability preservation with respect to avox reasoning was shown partially by Sebastian Brandt and partially by Meng, because Untalvi Suntisrivarapon is so hard to pronounce, so we call him Meng. And we also saw this extension of EL, which we showed in a paper, myself, Sebastian Brandt, and Carsten Lutz. And in this paper, we actually found maximal extensions that are tractable. So where we showed that if you add any other feature of OWL to it, then it gets X prime. And one of those is now a profile of OWL2. So profiles are sublanguages that are used for certain purposes. And this is used for efficient T-box reasoning, basically. And nowadays there are several highly efficient EL reasoners available. So our first one was called CEL, classification in EL. That was considerably faster than the SNOMED reasoner they had before. So the SNOMED reasoner was something we didn't really know about how it worked. We only knew that on the laptop of the main SNOMED developer, it took 40 minutes to classify SNOMED. So compute the whole subsumption. So we said, well, we can do better. And we applied for a project to do this, and after half a year we could already do better, but better meant 20 minutes, not 40 minutes. Yeah? And then other people started to implement our algorithm, basically. Snow Rocket was CEL implemented by someone that knew how to do memory management. And that got it down to, say, 1 or 2 minutes. And now ELK and conclude are in the seconds area, so maybe 10, 20 seconds. So this means when we started work on EL, a SNOMED developer that wanted to see how the hierarchy had changed by the changes he made could go for a longish coffee break till the reasoner was finished. And now he just presses the button and the result is there. So, nice development. Maybe not for the SNOMED developers, or for the coffee bar next to them. Okay, now, so going up, going down. Now we are going up again. Yeah? Well, see, yeah, waves. So we make it larger again. So this is now about horn DLs and beyond. This algorithmic approach that we developed for EL is nowadays called consequence-based approach. Why? Because it actually adds consequences of the T-box, which are other GCIs, and it adds them until no more can be added, and then you just show whether the subsumption relationship you are interested in is there or not. And this works in polynomial time. And this can be extended to other DLs, even non-tractable DLs, as long as they satisfy a nice model theoretic property. And this is called horn, being horn. And intuitively you can say that horn means that there is a kind of canonical model such that something follows from your T-box if and only if it holds in this canonical model. And the algorithm, you could also say, generates this canonical model, and then you just look at the canonical model. And horn, so you can do this if you don't have disjunction intuitively. Because if you have disjunction, you need to look at different possibilities, how the model could look like. And this works also in cases where you don't have tractability anymore, but then of course the canonical model gets exponentially large, for example. And an example is if we add inverse roles to EL, so inverse roles meaning you can turn around the role and also use it. And so we showed in our paper that if you add inverse roles to EL, then subsumption becomes X time complete. So it's bad again, in principle. But consequence-based reasoners, but the first one was by Evgeny Kazakov, turned out to be much faster on ELI than highly optimized reasoners for more expressive DLs. So this monster description logics that are handled by fact and razor and so on, they all can deal with inverses, but they on this ELI fragment, they are not as good. And it was also important because there was a medical ontology called Galen, which basically was in ELI. It had some other features, but the main thing that made it complicated and made it actually impossible to be reasoned about by these other reasoners was inverses. And Evgeny could show that his system could deal with it very fast. And now people got crazy because they said this consequence-based thing is so fast, yeah. So we want to use it for everything. So now they are even started to use it for non-horn DLs, where somehow you have to deal with disjunction, but which still works. And so there is this fairly new consequence-based reasoner, Sequoia, that can deal with a very, very expressive description logic in a consequence-based way, and it is usually, but not always, faster than the other systems. So now, so we are back up on very high. And this is the end of the journey. No more waves now. So let's just remember. So because it could be a bit dizzy now. So we have a great variety of description logics with different expressive power and whose formal and algorithmic properties are very well investigated. We have highly optimized reasoning systems. They are the formal basis for the R2 standard, and they are employed in many applications. And my claim is this was only possible because of the foundational work we did in the beginning and this investigation of the complexity, because we had a very good understanding which constructors are expensive, which are not expensive, and how to design good algorithms. But as you saw, this took a few up and downs before we were far enough. Okay, thank you.
Thank you, Franz. Questions?
So I actually have a question.
Yes.
So you went through these waves looking at logical reasoning, but there are other possible extensions like a probabilistic. You could try to handle uncertainty maybe through probabilities. I remember maybe 10 years ago, I remember seeing many papers on probabilistic description logic, something that I don't see now. Maybe I'm not looking at the right place. But maybe do you have an opinion about this? Is viable or feasible or not?
I mean, in principle, you have lots of extensions of description logics in non-classical directions. I didn't talk about those here. I mean, we have also worked on probabilistic description logics. There are also fuzzy description logics and temporal description logics, and combinations of those. Actually, we had one project where we looked at a probabilistic temporal fuzzy description logic. This was in a situation recognition setting, so where we observed the real world or an abstraction of the real world, and we wanted to find critical situations. And we needed all of that there. But in general, it turns out that this combinations usually are rather complex and not necessarily the computational complexity. So it might be that you are still at time or so for some temporal description logics, but still getting the implementation is much harder, and getting an efficient implementation is much harder. And there, I think for these extensions, we are not at a status as we are now for pure first order variant description logics, where we sort of could say we know everything. I mean, until the next application comes along that requires another constructor. Yeah? But there are some also implementations of things, but they are not so widely available, and it's not so widely agreed what is the right thing to do there. But you can do these extensions. They are just much more complicated than if you extend probabilistic propositional logic, say in a probabilistic way or so, because the existential quantifiers are nasty.
Thank you very much. I have two questions actually. The first one is, can you describe a very recent applications that use descriptive logics? Could be the web ontology language, just to know. And the second one is, how do you see the combining large language models with descriptive logics as future areas of research or applications?
I mean, the ongoing applications are medical ontologies. I mean, SNOMED still uses EL or extensions of EL that actually come from the fact that we realize that these extensions are still polynomial. At the moment, so what do we do? So, for example, we are in a project where we are trying to make cyber physical systems explainable, and there's one project that uses description logic to produce explanations to a user in handover situations. So the application there is mainly you have a drone that flies autonomously, and then something happens where the drone then says, I need assistance, so I don't know what to do. And then you need to, I mean, you don't just want to say user take over, you want to say user take over because. And there we have a very restricted variant of our situation recognition system put in, combined with some linguistic stuff that verbalizes what we find in this situation. So that's one of the most recent things. Otherwise, we are at the moment more working on making description logic ontologies more reliable, in the sense that we have methods to explain reasoning results. So if a user says, oh, why is this a consequence? I don't believe it. That shouldn't be a consequence. Then we say, yeah, but look here, you have these axioms, and then by these axioms you get these consequences, and here. But when the user still says, well, but that's wrong, then we know we need to change the ontology, right. And we have methods for repairing them. So in that sense, that's not a specific application, but it will help any application that works with larger ontologies, because they will always have errors.
And the second one is the combination.
Yeah, I try to avoid answering that. Well, I mean, my general observation is that what such tools like ChatGPT produce is very often wrong.
Right.
Yeah? It's nicely formulated but incorrect. And it would of course be nice to somehow put a logic layer on top of this to check whether at least it's internally consistent. Yeah? It might be that it's still claiming wrong facts, yeah, because it's inventing a paper that was never written or something like that. there probably a logical reason I cannot do anything about it, but it could, at least one could check whether the internal argumentation structure of the text makes sense. Now, whether this is a description logic task, we need to see. It is if the basic concepts that are used in the arguments can be described by description logic concepts, but otherwise it could also be something for argumentation theory, but logic-based argumentation theory. So this is, I think, where logic has its place in this setting, trying to make things consistent and avoiding errors.
More questions?
So, thank you for your talk. I'm researching in complexity, and you mentioned several times in your presentation issues of complexity. Mostly, I understood focusing on complexity, algorithm complexity, but also some other times in other contexts. So I want a little bit of comments on this, how you use the ideas, general ideas of complexity.
I mean, we definitely use what's called computational complexity. Yeah, so it's investigation of complexity classes, whether something is complete for a class. So the results, I told you, I didn't say this, but all these complexity results are completeness results. It's not just an upper bound, it's also, we have this as a lower bound. That's the computational complexity thing, but what we observe is, however, that in many cases, these worst case complexity results don't really say that you cannot use the language. So in principle, if you say if you have X time complete language, it's totally useless in practice because it takes exponential time. But we observe that in many cases, well-optimized reasoners behave quite well on the practical examples. We still don't know what are the properties of these practical examples that ensure that these algorithms work well, because you can always construct worst case things where they explode. And that's one of the things that we still don't understand so well. And basically, why, in spite of this high complexity, our algorithms work so well. We don't know. Other kind of complexity is, of course, also if you have one of these large description logics, then it's very hard to understand what such a concept description actually says. So this is somehow expression complexity. Yeah? So you have this expression and it has logical symbols in them, and how should you understand this? And there are some attempts to trying to explain what such a description means, also explain reasoning results, but we are not very far with that. So at the moment, I would say that the ontologies are written by an expert that knows both the domain and the ontology language, and the users that are not experts in the ontology language need to trust us, which is not so good. But that's the status, I would say. But we are working on explainability. But it's, even for these logic-based languages, it's not so easy.
Mm-hmm.
That is funny because people trying to use logic or description logics for explainable AI, and now you say that the explanations need another level of explanation.
Yeah, I mean, the thing is, in a certain sense, I always say we have built-in explainability. Why? Because we have this formal semantics. Yeah? This is, and we have the reasoning algorithms that are based on logical calculi, where basically the reasoning is composed of small intuitive steps, where every single step you say yes, that's okay. Now, okay, so this is nice, yeah, but what do you do if your proof has 2,000 lines? You cannot show this 2,000 lines to your user and say, now check every single step, and then you know that it really holds. Yeah? This doesn't work. Yeah? In that sense, even so you make it a bit easier to explain, but still you have a challenge. And that's what we actually do right now in a project. We're trying to say we have one project where we visualize logical proofs. And so you can zoom into the proofs, you can hide parts of it, you can get additional explanations when you click on a proof step and so on. But that, yeah, solves the problem if it's not too large, but the problem that too large proofs are just too large, we cannot solve, because we even have this, we of course also investigated the complexity of finding small proofs, and that has a high complexity. So this means in principle it's explainable, but in practice it's a lot of work, and I would say we are only at the beginning of that.
So my suggestion is that we continue over coffee. So we have a coffee break now. And Franz will be around for another week. So anyone wanting to talk, I'm managing his agenda, so just write to me. So thank you again.
Okay.